All right. Yeah, so thanks for introduction. I'm Yury, and I was, through my career, was working on brain-computer interfaces first for quite a while, where you analyze electric signals of your brain, and then I'm working in ASML, in machine control. But basically, through whole my career, I was fighting the two-language problem, where you implement something offline first in one language, and then you want to run it fast, and that you implement it in another language, they diverge, and this doesn't really work, and you debug this for a very long time. So, So you know the idea that when JuliaCon, that's kind of the solution for the problem, but it's not completely true, because there's some fundamental reasons why this was done before, besides the knowledge of language, right? Because in essence, offline analysis and runtime is slightly different tasks, which correlate a lot. So to address these problems, I will prototype in this FunctionFusion framework, which I will talk about today. But let's do some step back, and let's just talk about like simple example. Okay, let's imagine that we're making some boat control. That's not really, there would be no model, but you start with some simple model. You say, okay, this works. You have just a couple of inputs. You do something, that's your control. You send the real hardware to the water. Well, it doesn't work. You forget about a lot of things. Let's add more things, right? Your code starts growing. It becomes more complicated. At a certain moment, you say, okay, we need to make it now structurized, right? It's not a single function anymore. It's many functions. We test them, we run them, and yeah, this is keep evolving and getting more complex. So what do we do afterwards, right? We say, okay, now we need more layers. We need even more inputs. We need something that we can pre-compute before, right? You know, the model develops, it grows, and at a certain moment we even say, okay, this doesn't fit the time and budgets anymore, so we need to split it actually, right? And the typical technique there is you pre-compile something up front, or like pre-compute something, and then you run it on a real machine. And of course, when you do this kind of simulation in offline and in online, this now becomes a really big problem, because, well, if they implement it with different languages, it's even larger problem. But even if it's one language, it's still very different environments. Where do you want to analyze it, right? Probably during your analysis, you want to play with both things as a one item. And in the runtime, obviously, you run the only online part very frequently. So what does it mean? Yeah, there are differences between that. And this is the typical evolution of the language. And, well, quite often the straightforward approach is like, okay, we start duplicating our code. We start making the code which looks almost identical, but not really. Can we deal something with that? So let's go back. Let's take a smaller model, right? Let's, this is the diagram that you typically will make to explain it to your colleagues. But let's a little bit formalize it, right? Let's add the intermediate data steps here. Okay, now it looks like, okay, the green looks like a data, the orange like a computation, right? I name it differently. I say, okay, the green one is an artifact. And the artifact, it's not just the data, it's also a meaning. So when you name it, you don't name it, well, it's a mass. You name it, it's a mass of my boat. And if you have an anchor, well, it's a mass of my anchor, right? Same for computations. Computations, I name it providers, because they provide you those kind of artifacts. They may take some inputs. They also may take no inputs. Maybe they just can read the value from the hardware, for example, from the sensor. And for further discussion for the next 10 minutes, let's assume the providers are pure functions, so you can easily test them. That's very nice, and they have no side effects. This is very nice, because then you can say, okay, I have several providers which take some input, gives me some output, which means, okay, now I can connect them together, right, to get something meaningful out of it. I can construct an algorithm out of it. And this connection can't happen automatically, because if your system already knows well, in which terms you talk to describe your model, your domain knowledge. Okay, this is the inputs, this is the outputs. Just connect inputs to the outputs, right? It's very straightforward. So now talk about the package itself, FunctionFusion. It does exactly that in a nutshell, right? You can define artifacts. That's the syntax for it. It will be a lot of macros. Sorry for that, but it's in general just generates code for you, which does the job. So you can generate artifacts, and then you can construct algorithm out of it. It will automatically inline the providers inside, and and you will have your algorithm. It will work, but most nice thing of it, you actually have zero overhead of this, right? So now you have ability to declare in a declarative way to connect items in your system, and you don't pay anything for it. And when I say like there is zero overhead for this, it's literally zero. I have unit tests inside which checks that the assembly generated from the handwritten implementation is exactly the same as the one generated by the system. So this is kind of proven work. What else can we do? Well, the first thing, I'm drawing these diagrams, but it actually can generate diagrams for you. It can explain you what kind of system you are building. It can give you an overview of all possibilities of your system. You just specify all the providers, and it can show you what kind of algorithms you can build out of it. It doesn't do any validation. Or it can also take your actual algorithm and show, okay, this is actually what we deployed on a system, right? Maybe we made a mistake, maybe not. Maybe we just keep it for documentation purposes, right, or explanation. And of course, the providers in a sense, it's just the functions, right? It's just the functions with some metadata attached to it, so all this machinery can happen. What kind of providers else can we think about, right? Well, one of the simplest one. What if we have two artifacts which actually share the same data type, right? We can just say, okay, it's like domain name is different, but sometimes they mean the same. So, okay, can we just set the equal? Well, equal is named promotion. We just promote one artifact to another. You get it very easily. Well, sometimes you don't promote it automatically, the one to another. You say, okay, there could be conditions, right? This is how we do the branching in this system, right? Suddenly, there's not just a waterfall. It have branches. And this is a conditional artifact. Okay. What else can we do? Well, you probably describe algorithm in terms of certain effects. And sometimes you want to say, okay, this is kind of abstract algorithm, right? Maybe part of the computation I don't know yet. Maybe I actually want to leave it as a template so you can feel part of your computation. Maybe it's something like, I don't know, something landing on the moon and something landing on the Earth, and I need a source to compute the gravitational effects. They are different. Okay, maybe I don't put it as a constant. I put it as a provider which give me the result. So we can have the unimplemented providers. And of course, you cannot generate algorithm with something unimplemented because, well, what do you want to compute? You don't know what to compute. If you know what to compute, you substitute it. You just replace one with the other. And the beauty of substitution is it's not necessary to have only unimplemented. You can actually take your existing algorithm and say, okay, here I'm computing the wind effect. This is my new model. I have a stronger model for wind. I just replace one with another. And it will generate still same control system, but with different actuation on it, which is really nice. What else? Yes, this is the example of this kind of substitution. Grouping, it's a very trivial thing. Yeah, you probably want to group them together to exchange them, right? Maybe you're trying to build hierarchical models. We'll see later how it's going. But the difference between here, what I want to show is actually, okay, you can group them. It's a group. The difference between algorithm and a group in this idea is that algorithm just shows outputs and inputs, right? You can isolate it, right? It's a namespace. The group is not really a namespace. It's just aggregation of them. And you can access the sub-elements from the group, but you cannot access the sub-elements from the algorithm. In this example, well, for example, A2 is not available from the algorithm as an output, and it's available from the group because it's just a group. Sometimes we still want to say, okay, we have this nice algorithm, but we want intermediate data. For diagnostics, for example, right? It's a quite common topic that, okay, if something doesn't work on my machine, I want to just diagnose what happened, right? Well, usually we say, okay, this goes with the overhead. Obviously, you need to save the data, you need to extract the data. But it also usually comes with the overhead. Oh, we need suddenly to rewrite our code because we need to have an alternative solution which works slower because of the overheads. And then we have the production solution which works faster. How do we make sure that they are the same? Well, in this approach, it's very easy. You just say, take the production solution, open it up, remove the abstraction, take the samples that you need, and that's it. Right? It's guaranteed to be that if you change your production solution, it's guaranteed that the diagnostic approach would be updated, that the diagnostic algorithm would be working still in the same way as you intended. All this machinery sits actually on top of Julia, right? I'm using Julia a lot there. It's not really a compiler. It's kind of sophisticated code generator, and we leave all optimization for Julia, and apparently Julia can do this really, really well. The only thing I have to really invent is this context where basically Julia will understand that those variables, they have certain lifetimes, but it's like static call graph friendly, by the way, and all this stuff. On this slide, you can see, okay, you can define the context. It's actually automatically defined for every group, for every algorithm, and so on. You can create it by the default. It's empty, right? Then you can call algorithm, changing this context. By the way, this is again an example that you can produce multiple different implementations of the same algorithm, which have slightly different performance behavior or like external behavior, but they still implement the same algorithm, right? So in this case, it's an algorithm ban, meaning mutating, and you give extra argument, you give the context, and then in the context, you get everything which was computed, captured, and here you can see that, okay, we have actually input captured, we have result captured, and you can also see that, well, if you don't ask for the certain things, you don't pay for it, right? All other artifacts are enumerated, that they can happen in principle, but they will not happen. We can even go further and we say, okay, let's eliminate everything which is not computed, so even in the context level we'll not see it, but sometimes it's kind of not very handy. So there's just different flavors that you can opt in or opt out. And of course, we talk about the algorithms, but we build algorithms out of algorithms. And there is a possibility for that as well. You can say, okay, this is my algorithm, and this is how I provide the inputs, and this is how I interpret the outputs out of it, right? So if you have something which do Fourier transformation, maybe it's an algorithm which do the Fourier transformation or whatever the transformation that you think about, and then it's applied for data point A, data point B, data point C. You can even, like in this example, I showed that you can even nest the same operation one after each other, so you can build some recursive functions with a controlled depth of recursion. There is no cycles in this approach so far, just because I don't see a need at this moment with the things that I implement with it. But yeah, if you need a certain level of recursion, limited, you can just implement it. So far, it's this is what you already have in the package. And a little bit more, I will talk about it now, but there is one important concept which I want to come back and really go deep on it, is assumption that the algorithms are immutable. Because all this possible so far is on assumption that, sorry, immutable, I said immutable, pure functions, right? You can construct this easily if they are pure functions. If they are not pure functions, suddenly the order of execution becomes important. And this, as I mentioned, the main purpose for this is also build flexible but performant. And typically the performance, yeah, you have to mutate something, right? If you update matrix size of 1 GB, making the copy of this matrix for every single step in your computation is not really feasible. So in this example, I show you two possibilities, two possible operations, which makes it unpure and it makes it extra complicated, right? If we will look at operation 1, yeah, it's obvious. It just updates the data, right? It's important in which point of time we will update the data, but actually operation 2 is also tricky. Well, it doesn't really update the data, it produces the new data. But you know how it works in Julia, because it's a pure Julia code, right? If you update X, well, it will be updated. If you update artifact B in this case, the artifact C will be updated as well, because there is an implicit connection between them. So both of them are tricky, and in order to work with it, this is what I'm working now. First, you need to explain to your system that this is actually happening. And because analyzing this is kind of difficult, I made this audit provider sync macro, which calls your provider. You give an example. So I'm not relying on a static analysis. A static analysis of pure functions exists in Julia, but it's not like 100% reliable. It's very debatable what it can derive or not. And yeah, humans can derive this better. Or you can give it a sample, like in this case, you just give a sample of the input, and it will check what happens with the input. If input was modified, if output have connections to the input, if yes, it will just tell you that's the case. If no, it will tell you, okay, everything is good, this is a pure function. And if it's not a pure function, what can you do? You can actually, like in examples below, you can see, you mark that, well, it's a special syntax, right? It's not Julia, but I think it's kind of speak for itself. You mark that, okay, artifact A could be mutated by this, and artifact B belongs to artifact C, so you know these connections. As soon as you know these connections, you actually can tell the system to optimize for it, right? Now the system is aware, so let's look at the frame on the left, right? We have two computations which mutate the same artifact. Obviously, this will produce a wrong result. So what do we want to say? Okay, we inject the copy. The copy is implicit. You don't have to bother with it. The system will decide to inject the copy itself. And usually it just goes with like, okay, everything except the last one have to be copied. So it's fine. But if you change the problem slightly, right, now you have suddenly conditions, then it becomes important where the copy happens. And because the system already knows so much about your potential flow of execution, it actually can make a strategic copy saying like, well, there's a chance that we don't need to make a copy at all. That could be nice. And of course, on this diagram, you don't see the order of operations because it's data flow, it's not order. But it actually generates operations in such an order that this is ensured that this will work correctly, right? Eventually, if the copy have to happen, it will happen before the data is computed. And on a diagram 3, you can see, well, there's sometimes also the cases where you actually know upfront that even if it's a mutating operation, you don't need to make any copies because it will not interfere with anything. So you just omit the copies completely. This is what I'm working on now. It's not yet in a pull request, but it will be there soon. And this will solve a lot of problems with algorithms which wants to work a little bit faster, or maybe a lot faster. That depends on your algorithm indeed. Next to that, there is also like, yeah, what if we want to apply, what if we want to decide what to do on the fly? Sometimes it's very elaborate to decide based on the if statements, right? Maybe the conditions are really difficult. So here there is a special option, switch provider, and it takes a vector. And because of some limitations of the current implementation, it takes vector of data type, but actually the data type should contain artifacts, and it should contain one of these 3 artifacts. And then it knows, okay, I'll have a vector which contains those artifacts. I will create a vector which will contain those artifacts, but I will not compute them always. I will compute them in a lazy manner, because if somebody doesn't ask me to compute anything, I will just not do this. And this really intertwines with the mutability that I described on the previous slide, that it's another layer of optimization. Well, what if they are lazy evaluated? If we cannot predict upfront that they are lazy evaluated? What does it mean? Well, on this slide it's very simple, right? But if you think about it, the system can grow. You actually can find out that certain artifacts are computed always. You just have them, and the certain things have to be copied or not copied. So all this, the system just knows all of this, and what was before done by software people who are trying to optimize algorithm to dig this last 5% of performance, the system can do it for you. So you're busy with the more complex stuff, like how to make the algorithm. You don't bother with like, okay, how to avoid copies in my algorithm, because it will just figure out some solution which will work. What else? This is also a very interesting thing. It doesn't came originally, but when I started testing it, in the end was the question, well, are my computations correct? And sometimes you have to test it with data, etc. But sometimes I found that, okay, symbolics is really nice. They can actually capture the description of what you compute. And this have a lot of weird crosstalks about like what symbolics actually can do without this framework completely, right? But it's at least to enable this option, I say, okay, we introduce the templated artifacts. They type-based. So in the end, you just describe, okay, I'm replacing this type with maybe with number for the case of testing and with the float 64 for the case of runtime. So in your testing, you can actually run it. You can validate that symbolic equations that you wanted to have there are correct. That's what you expected. And in the runtime, it's just replaced with the floats and it works, right? And then you kind of sure that what you wanted to implement, like let's say you have a paper and there's only equations, right? There is no computation there. So you make sure that what's written in the paper is in your system, and then you just see how it works. And of course, beside that, there's a larger backlog of other features. As I mentioned, of course, there's a lot of things about this mutability optimization, etc. But visualization also can be fine-tuned and fine-polished. It's just to make it more robust for the end users. At this moment, it tends to generate huge graphs, which sometimes very difficult to understand. Certain things on those graphs quite often are not that important, right? Because you, from your domain knowledge, you kind of understand what does it mean. You want to emphasize on the things that are complex, and you want to hide the trivial things sometimes. So at this moment, there's no such a thing. It just generates the whole computation graph, and if your computation is large, then you'll really need to scroll. So there would be some improvements on that. And the other thing is some kind of interesting idea from this conference. Integrate bumper, because this thing, it can also reason about the scope of variables, right? It actually knows the lifetime of them. So you can say, okay, maybe I will use this knowledge to optimize the allocations. And bumper is already the package which can help you with that. And I think there is a good possibility to make this connection between the algorithm generation and memory allocation approaches. So yeah, but that's still on the roadmap. It's an early stage idea. That concludes my presentation. If you want to check the current implementation, FunctionFusion.jl on the GitHub, and I'm ready for your questions.
Great talk, thank you. Have you thought about first-class algorithms or algorithms that can modify other algorithms as part of the data flow graph?
No, not at this moment. It's intended to help you to generate the code which you will put on the machine. So at this moment, it's already evaluated. So.
All right, I might have missed this at the beginning, but I'm curious, how should I interpret the right-hand side of an algorithm definition where it says like bracket P1, P2, P3? What does that mean?
All right. Let me open something like, which slide? So in principle, okay, I will stop here because it's now group.
Yeah,
whatever.
any algorithm
it's the same.
right-hand side.
In principle, I have a chapter in the documentation which describes all this meta language which I put, and it have a logic. In this case, in the square brackets, you describe the providers which became part of it, right? So in this case,
So
we
it's
say
like the set of providers
it's a
available
set
to
of,
use.
in this case, it's a set
Okay.
of providers. There is a special syntax to describe artifacts. There is a special syntax to, well, maybe you want to just define artifact in line instead of using the artifact marker. You can just say, okay, I want this new entity. I want to name it, and this is the data type. So
Okay. Yeah. All
those
right.
kind of
Thanks. Thanks.
Any other questions from the audience? If not, let's thank our speaker once again for the wonderful talk.